Well, welcome back. This is the fourth part of our introduction to water filtration. And in this part, we'll go over some basic calculations for what's called the backwash velocity and the expanded filter bed, along with some just general information about granular media filters. And that'll be the end of our work on filtration. So let me share my screen with you. Oh, don't want to see that. Let's try it again. There we go. So let's start with what backwash velocity is and how we're going to compute it. We talked about what backwash was in the previous part of this course. That'll be part 3. So now let's do some calculations. So the backwash velocity can be estimated using this equation. This is called an empirical equation. What's happened is a lot of experiments were done with various types of media, and we looked at the data and we're able to fit a curve through it. You can see this is a power model. So let me first define the parts. So on the left-hand side is the backwash velocity, and the units of that will be in feet per second, typical units of velocity. On the right-hand side, we have what's called V sub s. V is velocity, S is settling. So this is the settling velocity of the media. And what that means is if you took a particle of sand or whatever other media you're trying to look at the backwash velocity for, and you dropped it in a column of water and you were able to measure its settling rate or its speed as it dropped through the water, that would be its settling velocity in feet per second. The alpha sub E is what's called the porosity. Alpha will be the porosity, and then E will be of the expanded filter. So this is one of your design variables. So there may be a typical porosity, and that porosity is a measure of the percentage of void space. So if something had zero porosity, it'd just be a solid. Water couldn't flow through it. So porosities may naturally occur somewhere around 0.3, maybe 0.25, somewhere in that range. And that tells you about 25 to 30% of the space inside the filter is open, void. And that's where water could pass through. And that's also where suspended material could accumulate. Now, the expanded part is what we would like it to be expanded to. So say, for example, if it was originally 0.35, I'm sorry, 0.35, and you want it to be 0.7, you want it to double, then you would know that the thing that you're looking for, your design variable, would be 0.7. And then you're going to raise it to a 0.45 power. So that's the tricky part when you go to the calculation. I've seen it numerous times. Students don't do that correctly, and you get the wrong answer. So let's go through that and see how that works. So once you have the backwash velocity, then you can estimate how much the bed expands. Here's another very strange looking equation. By the way, as we move towards the final exam, I would not expect you to memorize these equations. I will give you an equation sheet, and I'll talk some more about that as we move towards the exam. I'll actually make the equation sheet available beforehand so you can kind of know what you're going to need or what you'll see, or what you can have as we take the exam. So let's explain this equation. So first of all, L is the original depth of the bed in feet. So if we were in lab, typically our filters are either 6 or 9 inches. So it'd be 0.5 or 0.75 feet, and that would be the L part. So that's something you would know. The L sub E is the expanded. Again, E is expanded. So that's how big, if it's originally 6 inches, once we hit it with the backwash velocity, what will it expand to? Will it be a foot? Will it be a foot and a half? That's the expanded bed depth. Now down in the denominator, you have V, which is the backwash velocity, which we just computed, and V sub s, which is the settling velocity, which is what we had on the right-hand side of the previous equation. And those are usually things that you either computed or that you'll be given. And then there's alpha again for porosity, except you know it doesn't have the E subscript. So that's just the original porosity of the material. All right, so let's do an example. So let's say we have a situation and we want to compute or estimate the backwash velocity required to expand our sand filter to a porosity of 0.7, 70% voids. And then once we do that, we want to see how much the bed will expand. So we're going to have some data, and we're going to apply these to what would have been our filters in lab. And I know from our filters in lab that we're using sand, and the sand was 6 inches or 0.5 feet. That's the original depth of the bed. And also, we've measured the sand particles, and they're about 0.5 millimeter typical size. And we've done some calculations and some measurements, and we've found that the settling velocity of our material is 0.27 feet per second. So the first thing we'll, and the sand and the porosity originally is 0.35. So this is the original state, and you can see we're going to want to basically double that to 0.7. So the first thing we'll do is calculate the backwash velocity. So our right-hand side, there's our settling velocity, which was given 0.27 feet per second. And then there's our expanded porosity. That's the design. That was 0.7. Now, I've seen this happen quite a few times, so I'm going to tip you off. You want to first take the 0.7 and then raise it to the 4.5 power. I've seen students multiply the 0.27 times 0.7 and then take the power of that, and that's not the same thing. So again, 0.7 raised to the 4.5 power, and then multiply that by 0.27. So what I would do right now is I'd pause the video and see if you can make that calculation. 0.7 raised to the 4.5 power times 0.27. By the way, 0.7, the porosity doesn't have a unit, so your velocity should still have the units of feet per second. So pause the video and take a shot at the calculation. Okay, so let's say you've done that, and let's compare your number to my number. Well, I got 0.054 feet per second for my backwash velocity. Seems very small right now. So hold on to that. And next, let's see what that hydraulic loading rate would be. So I'm going to come back with my velocity, which is 0.05 feet per second. Doesn't seem very fast. But remember, hydraulic loading rate is volume per area per time, and we're going to convert that into gallons per minute per square foot. So this is a little trick you have to do. To get volume in the top, you'd have to multiply by a square foot. And of course, to keep the units squared or correct, if you multiply the numerator by square feet, you'd have to multiply the denominator by square feet. So this is kind of a little odd little step to get started. So you can see I've just multiplied the top by feet squared, could be 1 foot squared, and I've multiplied the bottom by 1 foot squared. So it hasn't done anything but changed my units. But you can now see I have cubic feet in the numerator, which is a volume, per feet squared per time. So now I'm ready to do my hydraulic calculation. So once I have it in this form, you can see I know that for every foot squared, there's 7.48 gallons, and there's 86,400 seconds in a day. So I've now converted this to gallons per day per square feet. And if you do that calculation, you'll get almost 35,000 gallons per day per square foot. Now it sounds like that's a reasonable amount of water. I mean, 35 gallons per day generated through 1 square foot of filter. So that's probably another simple calculation you'd have to make. You'll get to practice in a homework and maybe also on the exam. So now we have the backwash velocity, and we have the hydraulic loading rate. Now you might remember from the previous notes, that's about seven times larger than the regular filter loading rate. So the amount of water that was going through the filter in regular operation, it's about 7 times as much coming through in the backwash. So how much will our 6-inch filter bed expand for this during this run? Well, this is our equation that we used. Now remember, we've just calculated our backwash velocity. We were given the settling velocity, and we were also given the original porosity of the bed. And I also told you the bed was 6 inches, so that's the depth. We have everything on the right-hand side is known. So you put all those values in. Now, just like before, I suggest that you pause the video and see if you can make that calculation. However, before you do that, pay close attention to this value here. So you want to calculate this fraction first, raise it to the 0.22 power, and then subtract that from 1. I will warn you, not warn you, I will advise you that the denominator is not going to be negative. We're not going to get a negative change in the length. So again, now pause the video and see if you can make this calculation. Okay, hopefully you're back on and you have a number. Let's compare your number to mine. And I got 1.09 feet. So that means the bed, which was originally about 6 inches deep in backwash, expanded basically double the size to a little over a foot. Now, why would you want to know that? Well, if you know the bed's expanding to about a foot, then your backwash troughs or other parts of other components of your filter system could be located above that to keep you from washing your filter material out. You don't want to have to reload your filter material every time you run your filter. So you want to maintain that filter material as best you can. Okay, so I put this here. Don't really have any group problems to work on this video. But if you look in the class notes just below this, you'll see that I do have 2 problems for you to work on. And then once you've tried that, I have a video for the solution, and then I have a hard copy of the slide. So I give you a chance to work that out again. So you can work the problem that I just gave you here. Make sure you can do it. Work out all the bugs in your calculation, and then try it on those 2 problems. Okay, so traditional water treatment looks like this. You have your influent water coming in. You would hit it with some kind of coagulant, probably in a rapid mix up to maybe 30 minutes. Then you would go into a flocculation system for maybe 15 to 30 minutes, into sedimentation tank for a much longer time, maybe 1 to 4 hours, and then into a filter, and you can see the loading rates for the filter. You might even add an additional coagulant right before the filter, and then your effluent comes out. So that's what's called traditional water treatment. So under the force of gravity, the water will pass down through the media, and of course, all the flock particles will be collected. When the filter media becomes filled or full, we call that breakthrough. You start to get solids coming out in the effluent water, or the quality of the water comes up. It's time to turn off your filter. And as we talked before, then we'll backwash it. Now, filtration rates for the flocculation sedimentation are in this range here, about 2 to 10 gallons per minute per square foot. You know, when we talked about this before, about 5 is a typical design rate. Now, direct filtration kind of skips the coagulation and flocculation steps. So what happens is your influent comes in. You do have rapid mix of a coagulant, maybe some additional mixing, but then you go right into the filter. And then out of the filter, maybe some additional coagulation into the filter, and then coming out. So this is a little bit different system. The key components here are you remove most of the suspended materials are collected in the filter. There's nowhere else for them to go. There's no sedimentation system to help you remove the load. And the contact flocculation of the coagulant will occur in the actual filter. You saw one of the mechanisms in one of the earlier videos was flocculation inside the filter itself. So that's what's going to happen here. So there's been a lot of successful advances to help direct filtration become more usable. You can get these coarse to fine medias like we've been using, better backwash systems. They even have new coagulants called polymer coagulants that are very effective. And you can get filtration rates up now, you can see that are getting close to what were traditional filtration rapid sand filters. So there's different typical description of these systems. Again, the water will enter in the top into some kind of inlet flume, passes through the granular bed by gravity. The water is then collected in some kind of underdrain system. And here's just a kind of a picture of a large industrial municipal system. You can see that it's actually, there's one filter, two filters, three filters. So this would have three filters on one side. Typically on the other side of the building, there'd be another one. They share a basement system where all the pipes that bring the water in, backwash pipes, collection pipes, input pipes, maybe what's referred to as a pipe gallery. And then you can see below what a cross section of a typical system is. We've seen some of these before. I just thought I'd show you some different views. So during backwash, we know that the wash water passes up through the filter and washes out all the impurities. And that, as you wash it up, that expands the bed hydraulically. And then the water is collected in these troughs, and then it can be discharged out to be treated. Again, here's another example. What you can see here is the water now is maybe expanded. It's coming up. It could flow into the troughs and then be collected and taken out. And again, you can see a little bit too of different kinds of designs for the underdrain system that supports the media bed. So filters are usually placed again on both sides of the pipe gallery. You can get your inlet and outlet piping, all your backwash water piping, drains all together. Then the water is usually pumped out into some kind of clear well. Could be above ground, could be below ground. Here in Memphis, most of ours are concrete line tanks or concrete tanks that are below ground. Again, another system where again you can see there's a filter on one side of the pipe gallery, another. This one actually has a clear well underneath for storage. So there's a lot of different designs and configurations of these systems. So what is the ideal filter media? Well, it would look something like this. You would have large particles at the top, and as you go down, the particles would get smaller and smaller. So it'd give you a lot more pore space or open space at the top and tighter spaces at the bottom. So if you were a suspended particle, you might be able to come in and make your way down before you get trapped here. So in this case, the filter would fill from the bottom up, and you would get probably the best use of this material. It'd be great the first time you used it. Of course, this is all the same material. You turn it on, you backwash it, and what's going to happen is the larger particles will drop out. So this is, if you had a depth to pore space, you would see a lot of pore space at the top, less pore space at the bottom. Okay, so we backwash this thing and it tumbles around, and what happens? All the big particles sink to the bottom and all the small particles float to the top. And now you have exactly the opposite of what you wanted. You have little pore space at the top, which means your filter will fill up here at the top and then probably get plugged. And then you have all this capacity at the bottom that you haven't been able to use. So single media filters, this is a big disadvantage. So in dual media filters, we get a nice break in that we have two materials. We have a denser material on the bottom and a less dense material on the top. In our case, the top is anthracite coal and the bottom would be filter sand. The anthracite coal particles are actually much larger, and since they're lighter during backwash, they will float up to the top. Now the bigger ones still hit the bottom and the smaller ones go to the top. Same thing in the sand, but you do get a lot more pore space in the top of the filter after backwash than you did in the previous cycle. So now if you look at that plot, you can see, yep, I've got a little more pore space up here, even though I get more as I go down, and then it gets finer again. So again, this is trying to fill up, not all the way from the bottom, but we get a little more penetration into the bed and a lot more capacity to store suspended materials. So broadly speaking, the filter media should pass the following qualities. Sorry, you should be coarse enough to retain a lot of flock. You should be fine to prevent the actual suspended materials from passing through. The bed should be deep enough so you can have relatively long filter runs. And you want to grade the material to help with backwashing and cleaning. These attributes are not compatible. For example, fine sands that really retain a lot of flock have very short filter runs, so you need to kind of avoid those. And of course, if you go for super, super coarse, then you have a lot of capacity, but you wouldn't have enough fines, and the spin particles could pass right through. Very poor quality. So a filter media is defined by the effective size and uniformity coefficient. You may remember that from a week or so ago when we did the sieve analysis, and we did that to set up this work here where we could then characterize our filter. So remember, the effective size was the 10% of the material which was finer. We call that the D10. And the uniformity coefficient was the ratio of D60 to D10. And remember, D60 was 60% of the material was finer. And conventional sand filters, this is what you'd want for your effective size, about 0.5 of a millimeter. And you'd want your uniformity coefficient to be less than about 0.65. And sand filter beds with relatively uniform grain size can be effectively used as filter. Now, multimedia filters usually have anthracite and sand. Other materials have been used. There's been activated carbons and some other kinds of sands. And there's even multimedia filters that use a denser material, usually a garnet and finer, that under the backwash sinks to the very bottom. And again, there's been other materials used here. The main advantage of multimedia filters is to a single-use filter can be best summarized as you get longer filter runs. You can do higher filter rates, means you can produce a lot more water. And then, of course, you have the ability to handle large turbidity influent sources. The advantage of multimedia filters are due to the media size, the different specific gravities that we talked about, the lighter materials being on top, heavier materials sinking to the bottom. And of course, the gradation of that, making sure you get the right size. The lighter materials need to be coarser. As you go down to the heavier materials, they should be finer. And that's it. Kind of a odd stop point. But that's the end of our filtration stuff for the semester. Stop here. Please let me know if you have any questions, anything comes up. So we are getting close to the end of the semester. We just have a few more homework assignments, and then we'll be into the review for the final. So again, let me know if you have any questions. Go vote, and be safe and take care.